Assalamu alaikum wa rahmatullah. Welcome back. This is Dr. Muhammad Saad, and we are continuing our lectures on computer communications and networks. In the previous lecture, we talked about the Dijkstra shortest path routing algorithm. In particular, given a communication network as the one that you see as an example, so we have a set of nodes and we have a set of interconnecting links. Each link has a weight that may represent the distance, basically. Like if this weight is 7, it may represent the distance from B to C. So given a network like this, a set of nodes that represent routers and a set of communication links with weights, and we have a source node and a destination node, the question is, what is the shortest path from the source node to the destination node? In other words, what is the path from the source node to the destination node that minimizes the total weight along the path, that minimizes the sum of all weights along the path or the sum of all distances along the path? So we had a thorough discussion on the algorithm, right? And we have noticed that at the end, although we might be interested in the shortest path from a source to a destination, but at the end we can actually compute a set of shortest paths, not only one, but we can calculate a whole set of shortest paths from that given source to every other possible destination in the network. So as a byproduct, we calculate the shortest path from A to B and the shortest path from A to C and the shortest path from A to E and so on, from the fixed source to every other destination in the network. So we have seen that and we finished it. However, there is just one quick extension or a quick variation that we can talk about. Now, although we call the algorithm shortest path algorithm, but it is more general than just obtaining the path with the smallest distance. You know, if these weights indicate distances, if these weights here indicate the link distances, then applying the algorithm that we covered last time, that we covered in the previous video, will calculate the path with the smallest possible total distance. However, if these weights here, if these weights represent link delays, so if this is 7, if this 7 and this 2 and this 1 and this 4 and so on represent the delays on the respective links, let's say in milliseconds. So the delay to send a packet from B to C is 7 milliseconds. The delay to send a packet from G to H is 4 milliseconds and so on. In short, if each one of these weights represent the delays, then applying the same algorithm, exactly the same algorithm, the Dijkstra shortest path algorithm, will give you the path that has the smallest delay. So although we say shortest path, it is not necessarily the path with the smallest distance. It depends on the meaning of these weights, and the same algorithm gives us the path of interest. So we may want to get the path that has the smallest distance, so the actual shortest path algorithm, or we might be interested in finding the path that has the minimum delay. So all that we need to do is to use the link weights here, have to be delays, and we apply the same algorithm, and the path that we obtain is the minimum delay path. Finally, if each one of these weights is just one, if each one, so instead of different numbers 2, 2, 1, 7, and 4, and so on, if each one of these weights is just one, applying the same algorithm, applying the same Dijkstra algorithm in exactly the same way, will give you the path with the smallest number of hops. So the number of hops is basically how many links the path traverses, and all this is summarized in this slide here. So if the weight of each link is 1, then applying the same Dijkstra algorithm as it is will provide the path with the smallest number of hops. And if these weights, if the link weights represent packet delays over the links or average packet delays over the links, then applying exactly the same Dijkstra algorithm will give you the path with the smallest delay, or with the minimum delay, if you will, the fastest path. So the main take-home message here is that although we call the Dijkstra algorithm shortest path algorithm, this algorithm may give us different paths depending on the meaning of these weights. So now it's time to move on and go to our next idea. So in the rest of this video, we would like to talk about two practical routing protocols. When we say routing protocols, we really mean an algorithm to calculate the best path, in addition to a mechanism for the routers to exchange information amongst themselves so that they learn about the topology of the network and they keep updating the topology of the network so that they capture or they take into consideration dynamic and periodic changes that may happen into the network. We will talk about two protocols. The first one is called the distance vector routing protocol. We will finish it first, and then we will go to the second protocol. It is called the link state routing protocol. So we have two practical protocols. One of them is called distance vector routing, and the other one is called link state routing. In the rest of this video, we will talk about both. So the distance vector routing protocol, it's a dynamic routing protocol. As a matter of fact, it is applied by the routers of the network periodically. So once in a while, the routers repeat the overall process. They repeat the whole protocol so that they update the routing tables, and this happens always periodically, once in a while. Now, we know even from the previous lectures that routers maintain routing tables. Routers maintain routing tables. Routing tables usually look like this, as we are used to, even in the previous lecture in which we talked about connection-oriented versus connection-less packet forwarding. And in the connection-less case, we know that the routing table contains all possible destinations. In a column, we have all possible destinations, and for each destination, we have the preferred next hop towards the destination, and this helps a router make a forwarding decision. To complete the picture, it is not really strange to say that for each destination, we have the preferred next hop. So what is the next hop? What is the outgoing link towards that destination? And also, what is the total length of this path? What is the total length of this path from the source, which owns the table, until the destination, which is written in the destination column? So what you see here is not really new. So what you see here is the routing table that we understand even from 2 videos ago, right? So this is the routing table. So as an assumption in distance vector routing is that each router maintains a table which contains all possible destinations, so every other router in the network, and for each destination we have the preferred next hop, and we have the total distance or the total length of this path. Now, so this is a fact. Now, how do routers update the information in their tables? Of course, the information in the tables, so for each possible destination, what is the next hop and what is the total distance, cannot stay static. This cannot stay unchanged simply because the network topology might change, the network conditions might change, so the delays of the links might change from time to time. And we know also that these routing tables must be updated periodically. So the question is, how do the routers update these tables? In distance vector routing, in the distance vector routing protocol, the routing tables are updated by having routers exchange information with their neighbors. Neighbors are always other routers that have direct links connected to me. If I'm a router in the network, whenever there is a direct link to another router, that other router is considered a neighbor. So in distance vector routing, we exchange information in our routing tables with our neighbors, and I get the same information from my neighbors as well. Based on this, I will be able to update the information in my routing table. To be more specific, we know that the routing table contains all possible destinations, and for each destination, we have the preferred next hop and the total distance. What we need to exchange with the neighbors is only the part that's highlighted here of that table. So for each destination, what is the total distance? This is what gets exchanged with the neighbors, and this is the kind of information that I receive from my neighbors as well. And then based on this information, I will be able to update my routing table. I will be able to update basically what is now the up-to-date next hop towards each possible destination, and what is the up-to-date total distance or total length of each one of these paths. Now, how does this happen? This will be basically the remaining of our discussion, but before we go there, let me just mention as a fact that the distance vector routing protocol that we will explain in a couple of seconds was the original Arpanet routing protocol. So in the original Arpanet, the original father of the internet, this was the routing protocol used, and it was even used in the internet that followed, until it was replaced by the other routing protocol that's called link state routing. So we will finish describing distance vector routing, and as I just mentioned to you, this is the original routing protocol used in the original Arpanet and in the internet as well, until the year in which it was replaced by the newer routing protocol, that we call link state routing. And in this video, as we mentioned before, we will be talking about both. So distance vector routing, how does it work exactly? As we mentioned so far, and it's really nothing new, each router maintains a routing table which contains all possible destinations, and for each destination, what is the preferred next hop, and what is the total distance or the total length of the path towards the destination. Now, this distance, is it always the physical distance? I mean, is it always the actual length of the path? Not necessarily. So this distance metric here, as you see in the slide, this distance metric here may reflect the actual physical distance or the actual physical length of the link or of the path in kilometers or meters. Let's say this distance could reflect the hop count, so the number of hops, the number of links basically that this path has, or it may represent the time delay, so the delay to send the packet along the path. So this distance, again, it's a general term. It may reflect the actual length of the path in meters or kilometers. It may reflect the number of hops on the path. It may also reflect the delay. Usually in the internet we use delay because this is more basically, it's more informative. If we just stick to the physical distance, it might be the case that a longer link or a longer path has basically less traffic or less packets traveling over it. So sending packets over that longer path may be more efficient. So as a matter of fact, mostly in the internet, that distance reflects the delay of the link and the delay of the path. So what does each router initially know? Each router, before doing any calculation, each router knows the distance to its immediate neighbors. So if I'm a router in the network, I'm immediately connected to some other routers. So immediately connected again means I have a direct link from myself to that neighbor, and I know the distance to my neighbors. If the metric used, if we are working with hop counts, then basically the distance to each neighbor is just one, because the neighbor is directly connected. There is only one hop connecting me to the neighbor, so the distance to each neighbor is just one. More practically, if we're using link delays, and we can stick to this, so from now on we can just stick to the assumption that we're working with delays, right? So if the metric used is delay, if this distance metric means delay, then basically I can easily calculate or estimate the delay to my immediate neighbors as follows. So each router sends a special packet that we call the echo packet. It's a packet with a special format. It gets recognized by all of the routers as an echo packet. So what is an echo packet? I send a special echo packet along each outgoing link. So this echo packet will go to each of my neighbors. When the neighbors receive this echo packet, they will know what they need to do. They will need to reply with an echo packet as well, with an echo reply as fast as possible, so as much as possible without introducing any additional delays. And then using a timer, using a stopwatch, I can calculate, I can measure the time in seconds or in milliseconds between sending my echo and receiving the echo that comes from my neighbor. Now what I've just measured is 2 times the delay on the link. We call it the round trip time. The delay to send a packet plus the delay to receive a packet. If we divide it by 2, we have an estimate of the delay from me to the neighbor. Even to be more accurate, we can repeat this several times and then we get the average. Let's say we can repeat it 3 or 4 times and then we get the average. This is supposed to be, the result is supposed to be an estimate of the delay from me to my immediate neighbors. So what do the routers know initially before doing any other calculation, before exchanging any kind of information with the neighbors? What the routers initially know is the delays from themselves to their immediate neighbors. How can they estimate these delays? How can they measure them? It is really measurement using timers. So the way the routers do that is by sending echo packets from themselves to their immediate neighbors. The neighbors will reply with an echo response, and then using that timer, the router will calculate the round trip delay from themselves to these respective neighbors. This is the round trip delay, the round trip time, which is basically the time to send a packet plus the time to receive a packet. It is the time going back and forth along the link. If this time is divided by 2, as I explained earlier, if this time is divided by 2, we have an estimate, and I insist it's an estimate of the delay on the link, simply because we are dividing by 2. You know, the delay to go from A to B might not be the same as the delay to go from B to A, although we're talking about the same link, right? It depends on the amount of traffic going in each direction. If you have a highway, it is the same street, but the delay going from A to B might not be the same as the delay to go from B to A. Since we are dividing by 2, we are only estimating the delay on the link from the router to the neighbor, right? And to be more accurate, this can be done several times, and we get an average. In any case, this procedure is repeated periodically anyway, as we will discuss in the following slides. So this is what the router knows initially. Now, how does distance vector routing work? So after the router knows the distances / the delays to its neighbors, and this is something that the router will calculate or measure using a timer on its own. How does the rest of the algorithm work? How will the router update its routing table? The best way to explain the idea, which is what we have on this slide, the best way to explain the idea is using my own illustrative slide that has this illustrative figure. As an example here, imagine that we have router Y. This is the router that we focus on. You can imagine that this is me. I'm this router Y. And now I'm in the process of updating my routing table. This is one of the destinations here. So router I is one of the destinations. You may even assume that initially I don't know about this destination. So even Y here, or if I'm router Y, I might not be even aware of this destination I yet. But what I know is that I have 2 neighbors. Router Y has 2 neighbors, X and Z. So X is a router, neighbor to me. Z is also a router, neighbor to me. By sending echo packets here, what we have said here, by sending an echo packet to each one of my neighbors and receiving an echo packet from each one of my neighbors, I can estimate the delays on my immediate outgoing links here. So I have an estimate that the delay from Y to X is M, and the delay from Y to Z is N. So M and N here are the delays to my immediate neighbors. In other words, the delays on my outgoing links here. The link that comes out from Y going to X, and the link that comes out from Y going to Z. Again, M and N are measured by router Y on its own by sending an echo, receiving an echo, and using a timer, as we have explained. Now assume also that these neighbors X and Z, each one of them independently knows about this destination I. So X knows that the distance from itself to router I is equal to Xi, and this is an information that X knows. Assume that X knows about that. X knows that it can reach router I through a path which has a distance of Xi. That may represent also the total delay to reach I. Now, router Z also knows that it can reach destination I. Router Z also knows that it can reach destination I through a path which has a total distance of Zi. Now, what does Y know? What is the information available at router Y? M and N is the first piece of information that router Y knows, the immediate delays on the links, on the outgoing links, or the immediate delays to the neighbors. And this is something that Y measures on its own by using the echo packet technique. Now, what Y will know as well is these distances X, Y, and Zi. How will Y know about that? Y will know about them if the neighbors exchange this information with router Y. So X will send to Y that the delay from itself to I is Xi, and Z will also do the same thing. So X will send a table here, this kind of table that we have mentioned. Z will send this kind of table to its neighbor Y, which contains destination I has a distance of Zi, right? So in short, to summarize, X will send to Y information about this Xi distance, and Z will send to Y information about this Zi distance. If Y now gets information about Xi and Zi, what will Y conclude? what will y conclude? Y will conclude these two things. So y will conclude that its own distance to I is equal to m plus xi, right? M plus xi. Is this the best distance to I? Not necessarily. This is just the distance from y to I if we go through x. So if we send to x first and then to I, the total distance of that path is m plus xi. At the same time, y will also know that its own distance from itself, from y to destination I, is equal to n plus zi, and this is the total distance, or the length slash the delay. We know that length and delay basically represent the same thing here. The total distance from y to I through z is equal to n plus zi. So y has two alternative distances to router I. What do you think will y do in case it is interested in the shortest path? It will simply choose the smaller of the two. So it's a very simple calculation. Router y will simply choose the smaller of the two, and this will be the best way to reach router I as long as it has only two neighbors, x and z. If we have more neighbors, then we just have to choose the smallest of more than two options, right? And this is basically what we'll clarify in the complete example that will come next. We stick here to the main idea of the distance vector routing algorithm. So let me recap. Y has two pieces of information. Its immediate delays, m and n, which y will measure on its own by sending echo, receiving an echo, and using a timer. So m and n are known to y on its own using measurements by sending an echo and receiving an echo. Y will receive the following information from its neighbors. It will receive the distance xi from neighbor x. It will receive the distance zi from neighbor z. And then by doing a simple addition, adding m to xi will represent the total distance from y to I, but going through x. If we go through x, that's the distance from y to I. If we go through z, the distance from y to I would be n plus zi, and then router y will choose the smaller one of the two. Let's make a complete example here. Assume that m plus xi, so this first entry, is smaller than the second entry. So by adding m plus xi, this is a number and this is another number. We just add these two numbers. Router y also adds number n plus number zi, and then it will compare. Let's assume that m plus xi is smaller than n plus zi. So this entry is smaller than this entry. What will router y conclude? When router y now, according to this calculation, when router y updates its routing table, it will know that there is a destination called I. There is a destination called I, and the best distance towards this destination, of course, from y itself, because this is the table that is owned by router y. The best distance to reach this destination is m plus xi, because this was the smaller number of the two. And the next hop is x, obviously. The next hop is x because this calculation came from neighbor x as opposed to neighbor z. If n plus zi is smaller than m plus xi, then here in the distance entry, we would have n plus zi, and the next hop would have been z instead of x. Let's look at a complete example, and then we will continue. In this example, we have a network here. We have a network of routers. So we have routers A, B, C, D, E, F, G, H, I, J, K, L until L, right? These are the routers in our network. And then we have some links interconnecting some of the routers, as you see in this figure. So from A to B is a direct link, from B to C is a direct link, from B to G is a direct link, and so on, like from J to H and so on. Now, we are focusing, in this example, we are focusing on the calculation or the computation that happens at router J. So what happens exactly at router J? So that eventually router J will calculate its updated routing table. So what you see here is the final answer of this example. What you see here is the final answer of the example. Now, what is given in the example? This part here, what you see here is given in the example. But let's dig in a little bit deeper. So what does router J know? Router J knows the distances to its immediate neighbors. What are the neighbors of router J? It is A and H and I and K. By sending an echo by sending an echo and receiving an echo, router J knows the delays to these neighbors, to these 4 neighbors. This is what you see below here. So the JA delay is given to be 8. This is the delay from J to A. And the JI delay is given to be 10. So from J to I is 10. From J to H is 12. And from J to K is 6. So these 4 numbers are given in the question. These 4 numbers are given in the question. And these numbers represent the delays from J to its immediate neighbors. So if we just reflect on the previous simple example, these numbers 10, 8, 10, 12, and 6 are equivalent to the M and the N here, and they are given in the question. What else is given in the question? These 4 tables. This is the table that will come from A, the table that will come from I, the table that will come from H, and the table that will come from K. And by the way, calling it a table or calling it a vector, a table or a vector is equivalent. So the term vector in distance vector routing is nothing but the routing table that will get exchanged between the neighbors, and that's why we call the protocol distance vector routing protocol. Again, let's go to the example that we have. So router J will do its calculations to update its routing table based on 2 pieces of information. The first piece of information is the delay from J to the neighbors, which are these 4 numbers given in the question. And the second piece of information is the vectors that are coming from the neighbors. What is the information that is coming from A? We have mentioned before that in distance vector routing, routers exchange information. Routers exchange the routing table or the routing vectors with the neighbors. So we have information coming from each one of the neighbors. We have information coming from A, and information coming from I, and from H, and from K, right? What does this information look like? It looks like a complete routing table. So what you see here is the routing table from A to everybody else. This is what A knows. This is what router A knows basically at that time. This is the information that router A knows. It is precisely the routing table owned by router A. It contains all possible destinations. It contains all possible destinations and the total distances to these destinations. We mentioned that what gets exchanged is all possible destinations and then the distance towards each one of these destinations, which are given by these numbers here. Let's look at some examples here. So A is the source here in this table. A is the source. Obviously, the distance or delay from A to A is 0. Destination A is the same as source A, so the distance is 0. The distance from A to B is 12, from A to C is 25, from A to D is 40, and so on. From A to J is 9, from A to J is 9. As you see, the delay from J to A does not have to be the delay from A to G, even though we're talking about the same link. However, the delay in one direction might not be the same as the delay in the other direction. Basically, routers estimate these delays by sending an echo. It's just an estimate, as we have explained before. So what you see here in this vector is basically the routing table information that is owned by A, and A will send the whole thing, the whole table will be sent to neighbor J. And this, what you see here, is the table that belongs to router I, and this will again be shared with neighbor J, with router J. Again, what you see here in this table is for each possible destination. We just avoid writing the destinations again. So for each one of these tables, these are the destinations and these are the total distances. So from I to A is 24, from I to B is 36, and so on. From I to L is 33. What you see here are the total distances from H to all possible destinations. In other words, the routing table owned by H and the routing table owned by K. Let's put things together again. J has the final objective or the ultimate objective of updating its routing table, right? The way to do that, according to the distance vector routing protocol, is basically, to begin with, router J has 2 pieces of information. The first piece of information are the delays from J to the neighbors. The delays from J itself to the neighbors, which are given by these numbers here, 8, 10, 12, and 6. In practice, these numbers are estimated by J itself by sending an echo and receiving an echo and using a timer and dividing by 2, as we have explained several times. This is the first piece of information known by router J. The second piece of information are the vectors that are coming from the neighbors. So we have a vector coming from A, a vector coming from I, a vector coming from H, and a vector coming from A, which are given by these tables in this specific example. So to connect basically to the previous simple example, these numbers 8, 10, 12, and 6 are equivalent to the M and the N, and these tables here, these tables that are coming from the neighbors, are equivalent to the Xi and the Zi. Now, once router J has all this information, what does router J do? It will do the summation M plus Xi, N plus Zi, and then choose the smaller one, and then accordingly update the routing table. And this will be done for every destination. For every destination, we are adding this number plus the delay plus this number, which is M plus Xi. So we're adding this number plus this number, and we do it for each table, and then we choose the smallest one, and this will be reflected in the final updated routing table that belongs to router J. Let's focus on the example here that we highlight, right? Let's talk about it in details, and you will notice that the same operation is done for each one of these destinations. So for destination G, do you see J? And you see G, this is G, there is no direct link connecting them. So initially J might not be knowing about destination G, but once it gets this information from the neighbors, it will know about it. So let me talk about the actual calculation that happens. If we add 18 plus 8, 18 plus 8 is 26. What does this 26 represent? Of course, numerically, 18 plus 8 is 26, but what does that 26 represent? It represents the total distance or delay from J to G if we go through A. So if I go through A first, the total distance to G is 26. If I add 31 plus 10, it's 41. This is a typo, sorry. 31 plus 10 is 41. Now, the number 41, what does it represent? What does the number 41 represent? It represents the total delay from J to G if we go through I. Now, if we add 6 plus 12, which is 18, what does this 18 represent? It represents the total delay or distance from J to G if we go through H. If I add 31 plus 6, 31 plus 6 is 37. What does this 37 represent? It represents the total delay or distance from J to G if we go through K. So we have 4 alternative distances from J to G, each one going through its corresponding next hop. What do I do next? I choose the smallest number among them all. So 26 and 41 and 18 and 37. Obviously, the smallest number is 18. The smallest number is 18. Where is the 18 coming from? It's coming from neighbor H. So accordingly, we update the routing table at J. For destination G, the next hop is H. The next hop is H because the smallest distance was coming from neighbor H. The next hop is H, and the total distance is 18 because 6 plus 12 is 18. Let's do that for a couple of other destinations, and then I will have a couple of general comments before we move to the next protocol, which is the link state routing protocol. So let's look at destination B, for example. Let's look at destination B. What is the total? How can I get basically the updated routing table information? So let's add 12 plus 8 is 20. 12 plus 8 is 20. 36 plus 10 is 46. 31 plus 12 is 43. 28 plus 6 is 34. What was the smallest number among the resulting 4 numbers? It was 12 plus 8 is 20. So if B is the destination, for destination B, the next hop, the best next hop is A, because the smallest number or the smallest distance resulted in from neighbor A, right? So the next hop is A, and the total distance is 20. And we have our final table basically after we do the same calculation for every possible destination. Let's check L here. 29 plus 8 is 37. 33 plus 10 is 43. 9 plus 12 is 21. and 9 plus 6 is 15, which is the smallest total distance. So that's why for destination L, the next hop is K, because the smallest number resulted from neighbor K. So the next hop is K, and the total distance is 15. So the final answer to this question is the final updated routing table at router J, which is given by this table here. To be really complete, this table here represents the next hop and the total distance for each one of these destinations. So if you want to give the final answer as a standalone answer, you have to put a third column here, which contains all possible destinations A, B, C, D, E, F, G until L here. And then for each one of these destinations, this is the outgoing link or the preferred next hop, and this is the total distance. So this is the new routing table at router J. As you have noticed, we are doing a very simple operation. We're just adding the number in the table to the number below, and then we are choosing the smallest value, and this will be reflected in our entry. However, to avoid just a mechanical step or mechanical steps, we have been talking about the main idea so that we understand why does this work or where is this coming from. So what we just explained is distance vector routing. Now, let me mention a couple of comments here. We mentioned the comment that the delay from J to A may not be the same as the delay from A to J. So this was mentioned before. As another comment, router J never calculates the full path from itself to a router, to a destination. So when we calculated basically the best distance to destination G, did we calculate the full path from J to G, or was it just the next hop? So it's always the next hop, and we never calculate the path explicitly. So as opposed to using the Dijkstra algorithm, so in the Dijkstra algorithm, we calculate the full path explicitly, A, B, E, F, H, D. So we know what is the full path, but here in distance vector routing, we are only calculating the next hop, the best next hop, or the preferred next hop towards the destination. This is enough to do the optimal routing. So because I'm sending to the next hop, and then the next hop will have a similar table with the next hop and so on, eventually the packet will follow the best path, but I don't know about this path in full. It is just a comment on the side, especially if you want to compare with the next technique, which is link state routing. Now, as a third comment, what kind of information is shared among the routers here? Haven't we said that router J is receiving vectors or tables from neighbors AI, H, and K? So I receive information from the neighbors only. And when I send information, now in the next round, I can share this information as router J. I will share this information with my neighbors as well. So I get information from the neighbors and I share information from the neighbors. But what kind of information do I share? Didn't you notice that this information contains a full table? So at any given time, I'm sharing my complete routing table as much as I know. Of course, initially I know only about my neighbors. So since you see here full tables, by the way, since you see here full tables, so that operation that just occurred at router J is not an operation at the beginning of the operation of the network, but it could be later in time. But initially, routers know only about their neighbors. So router A knows only about B and E and J. So the initial table that exists at router A will not contain all this information. It will contain only the delay to B and J and E. The rest will not be known, or it could be represented as infinities, or they're just missing from the tables. Once we start doing this, we will learn more. So if J here knows only about its neighbors, initially it knows only about its neighbors, neighbor K and neighbor H and neighbor A and neighbor I. Once it gets information from the neighbors, it will learn also about the neighbors' neighbors. And then if we repeat this again, it will know information about the neighbors, and so on. Eventually, depending on how large the network is, I will know information about all destinations in the network, and I would have a full table just like the one that you see here. So this is also a comment that it takes time. It takes time for distance vector routing to converge to full information about all destinations in the network, because initially I know about my neighbors only, and my neighbors know about their neighbors only. So once we do one exchange and one update, I will know as a router, I will know about my neighbors' neighbors, which might not be everyone in the network depending on the network size. But if we repeat the whole process again, I will know about my neighbors, 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 and then my neighbors, 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 and so on, depending on the size of the network. Eventually, after some iterations, after a number of iterations in which in each iteration we are repeating a process like this, after a number of such iterations, I will have information about all destinations in the network. So basically, this distance vector routing protocol is somewhat slow. It converges a little bit slowly due to the fact that we exchange information with our neighbors only, and this is something that we will take care of in the next protocol, the link state routing. However, in terms of what gets exchanged, what kind of information gets exchanged with who, in distance vector routing, we are exchanging information about the whole network. As much as we know, we are exchanging information about the whole network with our neighbors. So let's keep that in mind, and we will continue this video with link state routing. Now, the second routing protocol we would like to cover in this video is called link state routing. We have just finished describing distance vector routing, which was in fact used in the original Arpanet until 1979. At that time, it was replaced by link state routing that will follow from this slide onwards until the end of the video. So the main reason for replacing distance vector routing with link state routing was the slow convergence time of distance vector routing. It took time. It takes time. If we use distance vector routing, it takes time until the router has full information about all destinations in the network. You know, in distance vector routing, initially, the router has information about the distances to its immediate neighbors only. After one iteration of distance vector routing, the router would have information about the distances to its immediate neighbors plus its neighbors' neighbors. It takes a third iteration, it takes a second iteration basically, so that the router understands the distances to its neighbors and its neighbors' neighbors and its neighbors' neighbors' neighbors, and so on. So depending on the size of the network, it may take several iterations of the distance vector routing until the router has all information about the distances to all destinations in the network. That's why we have link state routing. The main advantage of link state routing is faster convergence. As a matter of fact, we will describe link state routing using the following 5 steps. So we can say that one iteration of link state routing consists of these 5 steps that are implemented by the router. After the full 5 steps, after only one iteration of link state routing, the router would have a routing table which contains all destinations in the network. So after only one iteration, and the iteration consists of these 5 steps, the router has already all destinations in the network in its routing table. So basically, it converges faster. Now, this is the main advantage of link state routing versus distance vector routing, the faster convergence time. The full comparison, let's leave it until we finish describing link state routing, and then we will have a full comparison basically between link state and distance vector and the full trade-off between the two. So what are the steps of link state routing? We can summarize link state routing in the following 5 steps. So the router needs to go through these 5 steps. This is what we mean link state routing. The first step in link state routing is that the router needs to discover its neighbors. The router needs to learn who its neighbors are, who are the other routers immediately connected to it through a direct link. So discover the neighbors and learn their network address. What is the address of each one of these neighbors? Once I know about my neighbors, imagine that I'm the router that implements these 5 steps in terms of link state routing, in terms of the link state routing, or in the context of the link state routing protocol. After I learn who my neighbors are, I need to measure the delay to each one of these neighbors. Obviously, we know how to do that, as will come in the slide that will follow. We have to send an echo and receive an echo, and using a timer, I can basically estimate the delay to each one of my immediate neighbors. So first step, I have to discover who my neighbors are, what are their network addresses. The second step is to measure the delay to each one of these neighbors. So after these two steps, if I'm a router, it means I know who is directly connected to me and what is the delay to each one of these connected to each one of these immediately connected routers. In other words, what is the delay to each one of these neighbors. Now that information, the delays to my neighbors, I will put it in a special packet that we call the link state packet. That's where the name link state routing comes from. So that link state packet, in short, contains what are my neighbors, who are my neighbors, and what is the delay to each one of these neighbors. Now, what will I do with this packet? So this packet, again, contains the state of the links surrounding me, right? The links towards my neighbors. What are the delays of these links? This link state packet will have to be sent to all other routers in the network. So this is maybe an obvious contrast between link state routing and distance vector routing. When we exchange information, we will exchange it with the entire network. I will send my link state packet, which contains information about the delays to my neighbors. I will send it to all other routers in the network. Finally, once this step is done, and similarly, I'm also, as a router in the network, I'm receiving also information from the other routers. I will receive a link state packet from each other router in the network, which contains the delays towards the neighboring routers of these neighbors. Once I receive this information, it means I have the full topology of the network and I can compute the shortest path to every other router or every other destination in the network using a Dijkstra shortest path algorithm. So as you notice, link state routing is based on applying Dijkstra at the end. However, to apply Dijkstra, the router needs to have knowledge about the network topology, and building this knowledge about the network topology is done basically through the first 4 steps, in which the router discovers its neighbors, measures the delay to these neighbors, puts this information in a special packet called the link state packet, and then exchange this information with every other router in the network. Similarly, such information will come from the other routers, so I will have the full picture of the network, the full topology of the network, and then I can apply a Dijkstra shortest path algorithm. Once I do that and I have all the paths from myself as a router to every other router in the network, I can update my routing table as in the example that we have done on Dijkstra. So that's the summary of the link state routing algorithm. I trust you have an idea about how it works. However, in the following slides, we have pretty much one slide for each one of these steps. So steps from 1 to 5, which constitute to the link state routing protocol. So in the first step, we have to learn about our neighbors. A router needs to know who are the neighbors, who are the neighboring routers directly connected to it. How does this happen in real life, in practice? By sending a special packet called hello. So the hello packet is a special packet that the router sends along each outgoing link. So the router has some outgoing links. It will send the hello packet, and if there is another router connected at the other side of this link, it will reply also with a hello, which is a reply which contains the address of that neighbor. If I receive all these hello replies, I know who is connected to me, who are my neighbors, and what is the address of each one of these neighbors. So this is pretty much the first step, discover the neighbors. So how do we discover the neighbors? By sending a hello packet, and then the neighbor, if it receives this hello, it will reply with a hello packet as well, which contains the address of this neighbor. So this is the first step. The second step is to measure the link cost, the cost of the link towards each one of these neighbors. The cost is a general term, and what we usually do is to measure the delay to each one of these neighbors. So how is this done? Exactly as we have described in distance vector routing, by exchanging an echo packet. An echo packet, again, is a special packet. I will send the echo packet to each one of the neighbors that I've discovered in the first step. I will send an echo packet to each one of the neighbors that I've discovered in the first step, and then these neighbors will reply with an echo reply as fast as possible, again, as much as possible, trying to avoid introducing any extra delay. And then using a timer, I will be able to estimate, or basically measure the round trip time, So the delay to reach my neighbor plus the delay from the neighbor to me. So the round trip time, the time to send a packet back and forth on the link, divide by 2. This is an estimate of the delay towards my neighbor. Of course, we can do this several times, like 3 or 4 times, and then get an average with the purpose of getting a better estimate of this delay. So we have to measure the round trip time and then divide by 2. This would be an estimate of the delay to each one of my neighbors. So we have covered 2 steps: learning about the neighbors by sending a hello, waiting for a hello reply, which contains the network address of these neighbors, the network addresses of these neighbors, respectively. And in the second step, we send an echo packet to each one of these neighbors by receiving an echo and using a timer, and then dividing by 2, I have an estimate of the delay to each one of these neighbors. Now, what do I do with this information? I construct a link state packet which contains the information I've gathered in step 1 and 2. So building the link state packet is basically step number 3, which contains a summary of the information that we have gathered in steps 1 and 2. This is an example. So imagine that this is the network here. Do you see network of routers A, B, C, D, E, and F? You notice that router A has 2 neighbors, B and E, and imagine that the delays on the links to B and to E are 4 and 5 respectively. Now, if A sends a hello packet, to each one of the neighbors, it sends a hello packet to each one of the outgoing links. It will receive hello replies from B and E respectively, containing the addresses of B and E. And now after A sends an echo to B and to E, and then after receiving the echo reply using a timer, A would be able to calculate that the delay from itself to B is 4 and the delay from itself to E is 5. Now this information needs to be summarized. We will put this information in a link state packet. What you see here is the format of the link state packet. So this is the link state packet which was constructed by router A. So it contains the address of A itself, just to distinguish between this link state packet and the other link state packets that were constructed by the other routers in the network. So we have my own address. If I'm A here, I will put my own address in my link state packet. There is a sequence number simply because we are repeating this overall operation periodically. So after I do steps 1 to 5, which means 1 iteration of the link state routing protocol, after some time, I will repeat the overall process again by discovering my neighbors and measuring the delays. In that case, the link state packets can change, simply speaking, because the network topology can change. Maybe there is another router connected to me a little bit later, or if there is no other router, at least these delays can also change. So I have new information and I have to build a new link state packet with a new sequence number. So sequence number 1 would be the sequence number of my first link state packet. If I'm repeating the whole process periodically, I have a new link state packet. This will be reflected in the sequence number. So sequence number 2, 3, 4, and so on. So that basically we distinguish between the different link state packets at different times, simply speaking, because routers basically keep implementing or keep running this link state routing protocol continuously. It will repeat it once in a while, and so that they keep updating the routing tables periodically as well. So that sequence number is something that we just covered. The age, basically this age field will reflect how long the link state packet is allowed to live in the network. Obviously, once a link state packet is constructed, it needs to be sent to every other router in the network using a technique called flooding. And this is something that we'll talk about in the next slide, using a technique called flooding, in which that link state packet gets forwarded from router to router until all routers have copies of this link state packet, to avoid this link state packet from traveling in the network indefinitely. To avoid this to prevent this link state packet from wandering or traveling in the network indefinitely, we have the age field, which will be decremented by 1 every time the packet gets forwarded, so that when it reaches 0, this packet will be ignored. So it's a double check, it's a precaution that prevents basically the link state packet from traveling in the network forever. Since we have mentioned that, I think it makes sense that this age field, once the link state packet is constructed by its creator, let's say router A here, that age field is initialized with a high value, let's say 256 or a high value, and then once this link state packet starts to get forwarded, it will be decremented with each forwarding until if this reaches zero, and the link state packet is still in the network, it will be discarded so that we prevent this link state packet from traveling in the network forever. Let's recap. So this is the link state packet, which belongs to router A. It contains the address of A itself. It contains a sequence number, an age, which is initialized with a high value, and then it will be decremented as this link state packet is forwarded from router to router. And then most importantly, the link state packet contains the neighbors, right? B and E, the neighbors, and the delays to each one of these neighbors. This is actually our target. This is what router A wants to exchange with all routers in the network. Let's look at another example here. Let's look at router C. Who are the neighbors of C according to this network topology? The neighbors of C are B and D and E. So this is discovered by sending a hello in the first step, B and D and E. And then the delays 2, 3, and 1 are also discovered by exchanging an echo packet as in step number 2. And then this information will be put in the link state packet that belongs to router C. So we have the address of C itself, as usual, a sequence number and an age, and then the set of neighbors BD and E, and the delay to each one of them. That's what we call the link state packet that belongs to router C. Likewise, each one of the other router will construct a link state packet. So we have covered the first 3 steps of the link state routing protocol. We discover who our neighbors are. So the router discovers its neighbors, its neighboring routers, the routers connected to it through a direct link. It will measure the delay to each one of these neighbors by sending an echo packet. It will put this information that was gathered in step 1 and 2 in a special packet format that we call the link state package, which looks like this. Now, what is the step that comes after? Is to send this link state packet to every other router in the network. So this link state packet that we have constructed here, that was constructed by each one of the routers. Let's focus on router A. Router A wants to share this information with every other router in the network. So that link state packet needs to be sent to B, C, D, and E, and F. How does this work? So the link state packet needs to be distributed to the entire network, to all other routers in the network, and this works in practice using a very simple mechanism which is called flooding. So how does flooding work? I think the best way to explain it is on the figure itself. So A, in step 3, has constructed a link state packet which contains information about the neighbors and also the delays to each one of these neighbors. Now this packet needs to be distributed to all other routers in the network. How can we do this distribution in the easiest way? Simply speaking, router A will send this packet to the neighbors, so to B and E, and then the neighbors will forward to their neighbors, and then the neighbors will forward to their neighbors, and so on until eventually that link state packet is received by all routers in the network. That's how flooding works. So I send this packet to my neighbors, and then my neighbors will send it to their neighbors, and then these neighbors will send it in turn to their neighbors, and so on. There is just some small details involved here. So link state, basically flooding again works as follows. So the router sends its link state packet to its neighbors, and then the neighbors forward to their neighbors, and so on. But we have two additional rules that need to be regarded here. So first of all, when the neighbor forwards the link state packet, so A sends to the neighbors, to B and E, neighbor B will forward. When it forwards, it needs to watch 2 rules. First of all, when B forwards to its own neighbors, first of all, it does not have to send it back to the node from which it has received the link state packet. So when a neighbor receives a link state packet, it will forward to its own neighbors, to all outgoing links except the link from which the link state packet came from, so we don't have to send back to A. So this is number 1. Secondly, the neighbor will only forward if it's a new link state packet, and this is observed from the sequence number. Let's try to give you an example here. So let's backtrack and start from the beginning. A has constructed a link state packet. It will forward as part of the flooding process. It will forward to B and E. Now B will forward to C and F. E will also forward to C and F, right? So C will receive this packet twice, once from B and once from E. the first one that was received will be recognized as a new link state packet from the sequence number. It will be forwarded to all outgoing links except the one it came from. But when the same link state packet arrives again, so let's say the one from B arrives first, it will be forwarded to D, right? However, later on, it will be forwarded to D and to E to make more sense, to be complete. And then when the same link state packet arrives from E as well, it will be ignored by C because it has the same sequence number, right? So by using the sequence number, we make sure that each one of these intermediate routers, as part of the flooding process, forward the link state packet only once. Once it has forwarded the link state packet, it means it's done with this. It will not do any forwarding of a link state packet unless it has a new sequence number, which means maybe A has generated a new link state packet, because it is repeating the whole process again. And that new link state packet basically will have a new sequence number, which means it will be forwarded. So each one of these routers will forward a link state packet that has a particular sequence number only once, which basically means that eventually the link state packet has to reach each one of these routers, and then it will stop from being forwarding. Forwarding will stop, right? Just to make sure in case there is any error or something. That's why we have the age field as well. So if we backtrack, A sends the link state packet to B and E, B will forward to C and F, and E will forward also to C and F. But before each one of these routers forward, so before C forwards to C and F, the age field will be decremented by 1. So if this was initialized with a value 10, for example, before forwarding, the age value will be decremented to 1. So when this link state packet arrives at C and F, they will C and E. When B forwards the link state packet to C and E will observe that the age is only 9. 9 is still not 0, so C and E can still forward, but before forwarding, they will decrement the age in turn again by 1. It will become 8 and so on. Supposedly, the link state packet will reach all routers in the network because due to the sequence number, the router is forwarding only once. However, as a precaution, we still have this age field. So if by mistake the link state packet still exists in the network, it will be ignored by any one of the routers that will see this link state packet with an age equal to 0. It will be just discarded and we are done. So we have covered the first 4 steps. We have to discover who our neighbors are, who are our neighboring routers. We have to measure the delays to each one of these neighboring routers. We put this information from 1 and 2 in a link state packet. The link state packet will be distributed to all other routers in the network through a process called flooding that we have just finished describing. Once this is finished, what does the router know? So if A sends its link state packet to every other router in the network, meanwhile, A will also receive a link state packet from every other router in the network. Imagine A has received the link state packet from B, C, D, E, and F. Each one of them contains who the neighbors are and what are the delays. If we put this information together, it means router A knows the full network topology, who are its neighbors, who are the other routers in the network, what are the neighbors of each one of these routers, and what are the delays on these links. It means that router A constructs the full network topology. Not just router A, we're just focusing on A that does the calculation. However, the same thing applies for every other router. Routers will know the full network topology after finishing the step of distributing the link state packet. After finishing the step of distributing the link state packet, it means the other routers have my link state packet and I have received a link state packet from each one of them, which means I will construct the entire graph, or equivalently the complete network topology. What are all other routers in the network? What are all other links in the network with the delays on each one of these links? So I can apply Dijkstra shortest path algorithm. Imagine that A applies Dijkstra shortest path algorithm that we have described in the previous video. So A is able to calculate explicitly what is the best path from itself to every other router in the network, and then from this it will update its routing table. So from finding the paths, it will update its routing table accordingly, as we have done in the previous video in our Dijkstra example. So this finishes basically, this concludes link state routing or the link state routing protocol, but we have a couple of general comments, especially the comparison between link state and distance vector routing. So first of all, we mentioned already that the main advantage of distance vector routing is the fast convergence. So once a router has implemented these 5 steps, and these 5 steps together is one iteration of the link state routing protocol. Once an iteration is done of the link state routing protocol, a router already has a full routing table, or it has a routing table which contains already all other destinations in the network, so the convergence is faster, right? So this is the main advantage. In addition to this main advantage, we have some other differences, and let me mention 2 of them. First of all, since at the end of the link state routing protocol, at the last step, we calculate the shortest path using a Dijkstra algorithm, it means that these shortest paths are calculated explicitly. I know the path in full to every other destination in the network, but in distance vector, I can never calculate the full path. I just know what is the next hop on that path. So here I have the full path, which is calculated explicitly, but in distance vector, I know only about the next hop. So this is one difference. The other difference is what type of information gets exchanged and exchanged with who. Here, when we built the link state packets, it was distributed to every other network using flooding, right? So who exchanges with who? Routers exchange information with the whole network. Routers exchange information with the whole network, but that information contains only information about our neighbors. So what did A send to everyone here? It's link state packet, which contains only information about the neighbors. So let's put this in short. Routers exchange information about their neighbors. Routers exchange information about their neighbors with the whole network, and this is kind of the opposite of what happens, or the type of information exchange that occurs in distance vector routing, in which routers exchange information with their neighbors about the whole network. In distance vector routing, what gets exchanged? I get only information from my neighbors, not from everyone, just from my neighbors, but what I get from the neighbors contains information about the whole network, or at least as much as they know at that particular time, right? So this is basically the main difference between link state and distance vector routing, and this concludes our video, and we see you in the next video with congestion control. Assalamu alaikum wa rahmatullah.